The purpose of this short video is to introduce you to an algorithm, a software tool that's very, very commonly used across bioinformatics. It's called BLAST. BLAST is an acronym for Basic Local Alignment Search Tool. So remember, a local alignment is when we take a piece of DNA and try to match it to other pieces of DNA without trying to assume that it's the same length, so we can maybe find just small regions. That's what the local part means, small regions of our DNA that matches. There are several versions of BLAST. This is their main web page, and you can do everything on the web platform if you need to. They've got nucleotide BLAST, which are just comparing DNA to DNA. They've got a protein BLAST, and then they have versions that do translation. So if you have a piece of DNA that you have good evidence or you're fairly certain is a gene, often these translated versions are a little bit better at bringing back close matches because nucleotides are not as conserved as the amino acids. So this search will take your DNA, find the largest open reading frame. It will then translate that reading frame, and then it will compare it to all other proteins available online and return those back. And then there are subversions of those also. Okay, you can do genomes, and there are a whole bunch of other versions. There is also, the only other thing that I'm going to kind of highlight here is that there is a algorithm that uses BLAST. It's called Cobalt, but there's an algorithm that uses BLAST to do multiple alignments. And so in our next discussion, we're going to be talking in more detail about multiple alignments. This one is a progressive alignment. If you take a look at the information about it, there's a little bit of information, but we'll talk about iterative versus progressive alignment. So you can use BLAST algorithm to do multiple sequence alignment also. But more commonly, it's used to find matching pieces of DNA, similarities. And these can be orthologs or in some cases paralogs. And we talked about that idea of paralogy versus orthology. Now, most of the time for the processes that we're going to be doing when we use phylogenetics, we want to find orthologs. And so we want to be aware when it's possible that there are multiple copies of a gene, so it's a gene family with many different groups, that we're careful that we're finding the orthologs. Because orthology, remember, traces history of the species. That's where those orthologs diverged. Whereas paralogy traces the history of the gene duplication events. Okay, so just please be aware of that. And you can use BLAST on its platform here. Let me get back to where I was. Sorry. So you can use BLAST from the main platform. There are also many, many programs that implement the BLAST algorithm in their software, and Mega is one of those. So in Mega, I can highlight any sequence that I have. I can use the option either by search, it's under web, do a BLAST search, or I can use this little shortcut here. So I'm just going to show you some of the options here, and we should get very similar results for this sequence. So the default, if you're in DNA, is to do a nucleotide BLAST. You can also, there's some nice options here. You can give, if you're running multiple jobs, you can give your job a title so that when the results come back and you're running 2 or 3 BLAST searches at once, you don't need to try and keep track. You can have the name there. You could also tell which database you want to search, whether you want to do a smaller version. These are usually more for specialized applications. And you can even say, I'd like to find, I'm searching a Drosophila gene here. I'd like to find a match to this, but in butterflies. You can use common names or scientific names. And so you could say, find me the closest match. And in fact, I'd like butterflies, but maybe I don't want to include one group of butterflies. So I'd say I don't want the Pieridés, as I want a butterfly that's not a Pierid. So you can modify this search fairly easily, and it really is a nice way to find very specific genes. Now there are other options here. You can even change some of the search parameters. We're going to do a quick search here, and then I'll take you through kind of what the results of a BLAST search work. Now these are not as critical. Most people leave these on the default, so you probably don't need to mess with those a whole lot. Okay, so let's see if we can get the search to run, if my internet connection is going here. Maybe. Okay, here we go. Now, by default, when a blast search begins, you get a little bit of a countdown and it refreshes. Oh, I might have to restart this one. Let's just go ahead and do another quick one. I will just eliminate butterflies and not, or just do a search among the butterflies and not worry about, let me close down some of these other windows. I don't know if that's what's causing it. Okay, so blast search. Let's eliminate, or sorry, search only in the butterflies. Here we go. Okay, sorry, I had a little bit of an internet connection issue. So you'll get this window that comes up saying the search has been submitted, the time it was submitted, the current time, and then every few seconds this window will refresh. If their servers are very, very busy, it sometimes will take a minute or two. The more complex searches, like when we're doing the translation searches, will take longer. So the results will look something like this. You've got at first a list of all of the matches, a description. And so you have the name of the sequence. The species usually comes first. If it says predicted, that means that it was a DNA sequence and they haven't done any experimental procedures other than just translating the DNA sequence and comparing similarities. They haven't done anything additional to confirm that this is actually that protein. But those predicted ones, those algorithms they use and the comparisons are very, very good. So predicted is usually, 99.9% of the time is yes, okay, it's that gene, and they've identified it. And there are a number of values over here telling you how much your sequence matches the sequence that you've searched. The E value, the lower this number is, the better the match it is. So the two ones you want to look at are what percentage of your search the match covers. So here we're only covering 22%, but that 22% that matches has a very, very low, this is 8 times 10 to the minus 58, so really, really high low, but a very good E value. And over that region, it's 81% similar, okay? So realize that we may not have a perfect match, but this is the very best match that it could find among the butterflies. Now, if I go back and I do this search without constraining it, so let's just go back. I'll edit my search here. And I'm going to do it without giving it any constraints at all. Now, because this is a sequence that I downloaded from this database from GenBank, of course, it's going to return this sequence with 100% similarity. 100% match, 100% similarity, and the E-value will be 0. And then there will be other sequences, and because this is in melanogaster, there are many, many DNA sequences available for that species and also closely related species. You're probably going to see some very, very high E-values and full coverage just because there's been a lot of work done. If I'm blasting a species that's less well-known, that's less worked on, then I might get a different range of values as a result. Okay, so occasionally the machine will kind of not update itself. You can usually refresh the screen and get back to the blast search. So let's see if we can get the results here. There we go. Okay, so in addition to these, you can click on any one of these sequences and it will take you to an overview of the alignment is the first thing it takes you to. Bring that up. Okay, so it brings you to an overview of the alignment. And again, because this is 100% overlap, 100% similarity, we're going to have a match for every single base pair, right? So if you then want to work with this sequence, you can click on a link to that sequence and download it or look at it or do whatever you want to do. So this is a really, really handy way to interface and find similar sequences. Now, you have the alignments. You also have a graphic summary, which shows you in blue your query sequence, and in red all of the matching sequences. So notice all these other ones match it pretty much exactly. And then there are some areas where we're a little shorter and some gaps are inserted. So we're starting to get into the more distant species and the ones that are a little bit different. The taxonomy will also, of all the sequences, this is not something that you'll use really quickly. And then you have this idea where you can look at a multiple sequence alignment view. So that's going to load up here. Okay, so what you see with this multiple sequence alignment, it's the first 100 matches and where they match. And everywhere it's red means that it's a really good match. If it's gray, it means there's lots of mutations and differences, but it was alignable according to the algorithm. And then if there's white space, it means there's a gap. And so I think you can even zoom in here. Let's see. I haven't used the multiple sequence alignment a lot. And for multiple sequence alignments that are going to be used for analyses like phylogenetic analyses or population genetics, usually people use other algorithms, but there is one that's available via BLAST. Okay. So one last thing I just want to point out, let's go back to the main BLAST webpage here. You can also download the BLAST algorithm. So you can download it, put it on your local computer. You can search local databases, which is helpful sometimes. So for instance, if you have a transcriptome and you want to find a particular gene in that transcriptome, you can download the BLAST algorithm, and then rather than using the online database as the target for your search, you can use your local database, that transcriptome, and say find a UBX gene that comes from Drosophila, find the closest match in your local transcriptome. And so you can download that here. Implementation is command line, so it requires a little bit of practice and some use, familiarity with the way to do command line. So we won't be doing that in this class, but you might see that in some applications depending on what your graduate work entails. So BLAST is a very widely used, very useful and flexible algorithm. We'll be using it primarily as this attachment here in Mega, as we use Mega, but just be aware of it. It's related to sequence alignment. It does local alignments, and there is some ability of it to do a multiple sequence alignment, but there are other programs that are more heavily used and widely used for multiple sequence alignment, and that will be the subject of our next discussion.